Kind of a crazy place is this?
All right, say I wanted to price an unusual option that had a payoff at expiry that looked like this. So it paid nothing if the stock finished below 10. It paid on this line, so this looks like the line S minus 10, if the stock paid between 10 and 20. This sort of looks like a call, but it caps out at 10 bucks. So if the stock finishes anywhere in between $20 and $70, the option pays $10. If the stock finishes greater than $70, the option pays nothing. So we know, since the lowest value the option could ever be is 0 and the highest value the option could ever be is 10, that the value of this option before expiry has to be something in between 0 and 10. So we could use our formula 8.7, and this would be like the traditional way to start this. So we'd have to pop that payoff in there, and what does that mean for us? Well, I'd need to be integrating 0 from this, integrating the payoff function 0, so before 10. So I won't start that. I'll integrate the function s minus 10. Let's make this, shrink this so we can see. I'll integrate the function here s minus 10 payoff from 10 to 20. Then I'll add the payoff of 10 from stocks from 10 to 70 and 0 afterwards. So I'd have to do these two integrals. And we know how to do these two integrals. Notice I can't just simplify this minus 10 and this 10 because they're over different intervals. We could do these two intervals using the technique from the previous video. But what was the previous video was like 50 minutes long. We'd have to do two of them. We don't want to do that. The other way, the better way, is to notice that this option, although it's weird, is still made up of flat lines and slanted lines. So we could build it out of our sort of store-bought options. So here's one idea. You could say it's a call starting at $10. Now if I just had that, that would shoot off this way to infinity. So I subtract, or I short a call at 20 so that that sort of cuts it off. So any stock value that's, let's say, 30, this call with exercise price of 10 would have a value of 20, and this would have a, with exercise price, this call option with exercise price 20 would have a value of 10, 10 minus, or 20 minus 10, it's 10 all the way through. But I need to shut it off. So I'll short 10 binary calls with an exercise price of 70. So I could build this expression using calls and binary calls. And each one of these call formulas and binary call formulas, we could just use the off-the-shelf pre-derived formulas. We could, it's not a unique way to express this payoff function. We could express it like with puts. We could say we have 10 binary puts. So 10 binary puts with exercise price is 7. That would be flat here and then up to 10, because it's 10 times the $1, all the way across. So I need to sort of subtract this piece. We could short a put at 20 and then buy a put at 10 to sort of stop. If we short a put at 20, then this is going to go down to minus 20 here. We want to stop that, so we want to buy a put at 10. These two, if I were to graph these two payoff functions, they're exactly the same. So if a function has the same, if a option has the same payoff function, then it'll have the same formula, because all we're going to be doing is integrating this payoff function. And let's use the top then. So if I want to use this top formula, that's a call with exercise price of 10, short a call with exercise price of 20, short 10 binary calls with exercise price of 70. Here's our pre-made formula for a call with exercise price of 10. Notice the D1 and D2, they have E's in them, so I have to make note that I'm using E equal to 10, the exercise price equal to 10, to calculate this D1. To short this call with exercise price of 20, well, I have to use different D1s and D2s. Here's our E formula. And then finally shorting our 10 binary calls. If I work this formula out, I'm going to get the value of that call as a function of stock and time left. That's what's my point. That's a lot easier than doing this integral. We've already made these pre-built formulas. Now we can use them. The only time I have to go back then to this formula 8.7 and actually do the integration is if someone is asking me. If the professor's asking you to, derive a particular formula, then, I need to go back to that formula. Or if the payoff function is somehow not built of flat and straight, slanted lines, if it has some kind of a curve in it, then we can go back to that integral. Here's a question. What happens if the integral I get when I plug in this weird curvy payoff function that I can't use the store-bought flat functions for? What if I plain can't integrate it? What do I do then? Well, you can always integrate it with some numeric technique that you learned in calculus, like Simpson's rule or trapezoid rule or Riemann sum, Monte Carlo integration. There's numeric ways to integrate things, so you can always get a number for it.
He's destroyed my life's work.